Hello, you beautiful people. So we are still at the Recycle Reactor from worksheet number 5, and the last part D, was about creating a little simulation program with the Euler Scheme. And last time I showed you that basically the programming was quite like you know it from the plug flow reactor, but there were two things. You have to correct for the volume flow and you have to correct the conversion. And in the worksheet I put in some equations, but as I understand from some emails that I got from you, that it was that you have some problems with this equation. So that's why I want to give you a little bit more information about how this can be found. Okay, so let's start. We have our plug flow reactor. So here is the plug flow reactor, and then we have the recycle stream here. And so you have the inlet mole flow of component A, and here you have the outlet mole flow NA, and here you have the recycle ratio, so the volume flow, let's say, okay, this is here you have the recycle ratio is equal to 5. So, and normally if you just make a big boundary, if you are looking at your, so if you're, actually I wanted to put it here. So if you make a balance like this, then it's no problem to calculate your calculate your conversion. So XA is just the outlet, or it's the inlet flow minus the outlet flow divided by NA0 by the inlet flow. So, but what happens inside the reactor? If you want to know your conversion somewhere inside the reactor, then you have a problem, because which color? Okay. If you have a recycle ratio here, this means that your NA recycle, this should be, oops, not 5, let's write R. This is R N dot A. So this means if you have a recycle ratio of 5, this means that if you, for example, here you have a mole flow of 1 kilomole per hour, this means of component A, this means with a recycle ratio of 5, this means that 5 moles per hour of component A are sent back to the inlet of the reactor, and this means you have a much higher mole flow of component A inside the reactor. And yeah, what does it mean? This means that the outlet of your reactor, there you should have R plus 1 times the outlet mole flow of your component A. So this is basically just the definition of the recycle reactor. So you have N dot A leaving the reactor, and then you have R times the mole flow leaving the reactor you are sending back. And if you say, okay, this is 1, this is R, then you must have R plus 1 times the outlet mole flow of component A. You must have, this should leave the reactor. And yeah, if you now want to calculate the conversion at some space here in the reactor, then you must take into account that your mole flow here inside the reactor is much higher than the one leaving the reactor. And so how can you do this? What is your naming convention for this. So let's say, oops, what color? Let's say let's say we go here at the outlet of our reactor, and there we have our n dot A out, and this must be equal, so n dot A out must be equal to r plus 1 n dot A, or we can write vice versa, n dot A is the same as n dot A out r plus 1. So and this can be applied for every position inside the reactor. If we, for example, go to this position here, then we can say, okay, this is our position I. So we are discretizing the reactor, and we are say, okay, we have different slides, and this should be our position I. And if we say, okay, let's assume that our reactor already finishes here, then we can say, okay, a part of this mole flow must go back to the inlet, and the other part should leave the reactor. So just like we did here at the end, we can say it for every position inside the reactor. Maybe it's wrong, it's a bad idea to put it there. Let's go here. So part and then you can say, okay, if I want to know my conversion inside the reactor, then it's just your conversion at any position inside the reactor, at any position I, is the same as the inlet mole flow, and then you have to take in minus n dot A. So in the script I wrote out, you could also say, okay, this is not my outlet, but it should be something like inside the reactor or whatever. You could, maybe it's more meaningful to write reactor, but this is, then it becomes so big. So let me, and this should be the same as n dot A inside the reactor. Oh, my life. So, and this you have to correct by r plus 1, and then you can divide it by n dot A0. So with this, you make sure that you compare the same amount to each other. So this would be, if you cut your reactor at any position here, then let's say n dot A reactor. So this here, the one going there is n dot R n dot A reactor, and this is n dot A reactor over r plus 1. Oops, this is r over r plus 1. So, and with this you can calculate the conversion inside the reactor at any position. Okay, so maybe just to give you an example, if you say, okay, this should be something like, let's say, green one, this should be something like 5 or whatever. I skipped the units. So this should be 5, and here you have, for example, this should be 4 or whatever. But then you have a recycle ratio of 5. This means you have 20 going back, and then so inside the reactor you have really big values. So your mole flow should be at the inlet, your mole flow should be like 25 or whatsoever. And if you want to use the conversion inside the reactor, then you would get really weird results. So for example, this should be 5, inside the reactor could be 15, then you have 5 minus 15 divided by 5, then you have a negative value bigger than 1, and this is absolutely meaningless. And that's why you have to correct your volume flow inside the reactor, or your mole flow inside the reactor, by dividing it by r over 1. Okay, hope this becomes more clear now. For my MATLAB code, I rewrote it. So I was just writing there, it's r plus 1 times n dot a0 minus n dot a inside the reactor for every position I over r plus 1 n dot a0. Okay, if you look at my MATLAB code, so basically this is what I did here. So this is slide 10. Okay, so this is, hopefully this helps you to understand my MATLAB code. The next thing is the volume flow. Again, we have here our reactor. So we have here our initial volume flow, we have our outlet volume flow, and here we have V recycle is R times this one. Okay, and we have our outlet conversion, we have our inlet conversion, XA in to the reactor. And now let's have a look at our volume flow. Okay, so if this should be volume flow at the inlet. Okay, our volume flow at the inlet should be just the mixture of the volume flow coming newly to the reactor plus the one that is recycled. So this is V dot 0 plus R times the outlet volume flow, and the outlet volume flow can be written in terms of the conversion. So V dot 0 plus R times initial volume flow 1 plus epsilon and the conversion. Okay, with this you can put your initial volume flow, you can put it in front of your expression, is 1 plus R times 1 plus epsilon XA. Okay, and this is conversion conversion at the outlet. Okay, and then you need to know a little bit about the reaction. We had the additional expression, we had our XA in is the same as XA times R over R plus 1. Okay, and then we can use it. So I put now, let me rewrite it. V dot 0, 1 plus R plus epsilon R XA. So, and if you look here, then I can just add here this by R plus 1, and then I multiply it by R plus 1. So, and then I have to close the big bracket. So what did I do here? I just put in the R. I put here into this expression, and then I've said, okay, let's add R plus 1 above and below the line, and then you can say, okay, this one, this is just my XA in. This is my conversion at the inlet to the reactor. And with this, I can just write my volume flow. Volume flow in is the volume flow at the initial position. And then, let me write it, 1 plus R plus epsilon XA in times R plus 1. So next slide. My inlet volume flow is initial volume flow times R plus 1. So, and then I have R plus 1. Oops. I have R plus 1, I have here, and I have it here. So I can put it in front of my brackets. And then I end up with 1 plus epsilon XA in. And this, you can reformulate this for in general. It's English, so I start with a small letter, general. The volume flow at any position I is the initial volume flow times R plus 1 times 1 plus epsilon XA at any position inside the reactor. Okay, and this is basically what I have here. This is slide 12. So this is the initial volume flow times R plus 1 times 1 plus epsilon XI. And XI is the conversion at any position inside, or at the position I inside the reactor. So this is the term that we have here. Okay. So basically what you do is you treat your total volume flow is the initial volume flow multiplied by R plus 1, and then you just have to correct it with the effect of changing density inside your reactor, and this depends on epsilon and your conversion. Okay, and what did I do in my MATLAB code? I tried to program it hopefully in a quite easy to understand way. What I said, okay, I have here, this is basically a plug flow reactor, and what I do is I said, okay, I start here with my initial values or inlet. Here I calculate my inlet values and then I'm just using the Euler Scheme for the calculation inside the plug flow reactor. Here I have all the big volume, all the big mole flows and volume flows and whatsoever. And then I say, okay, what is, then I have something like x out. I have an outlet conversion, and then I said, okay, I have a recycle ratio, and I put the values from here I take with the recycle ratio, put it back to the inlet, and then start my calculation again. Then I get the outlet conversion, and what I then just do is x out from something like, now it's iteration, so let's say iteration plus 1. If this is so what I do is I calculate my my conversion at the outlet of the reactor, and so I have here an external iteration loop. So this means I calculate my conversion here, and then I always check, okay, how is it in my current iteration and how is it in the iteration before. And if they are the same, then I stop my iteration and then I say, okay, now I have a converged system. If I have a difference between my old outlet conversion and my new outlet conversion, then I have to make another iteration loop until I get a constant value for the conversion value here. For those of you who had Simulation verfahrenstechnischer Prozesse, so there I showed you DVSim. It's the process simulation program. So in DVSim, this would be something like a recycle block. So what I did in my MATLAB code is just to implement something like a recycle block to make sure that I get the correct value for my plug flow reactor. Okay, then let's have a look at my MATLAB code. Yes, I want to keep it. There's MATLAB. Okay, so let's first have a look at the pictures that I get. Okay, so this graph you already know from the previous video. Here you can see the conversion curve, or conversion versus 1 over R curve. This was just to make sure that I'm simulating the process correctly. Then here I have concentration profiles, and I also have the mole flows here. And here you can see that your mole flow from component A, so this is really a big mole flow. So you have like 75 kilomoles per hour, going down to like 45 or yes, 45 moles per hour. Okay, then let's have a look at my MATLAB code. I'm just initializing the inlet concentration. Then this is my initial volume flow at the inlet. I have the rate constant K, I have the epsilon, I have my target conversion, and I have the recycle ratio. So nothing special about it. Then I say what is my inlet mole flow, and this here I just have for the analytical solution. So here I have the analytical solution, and inside the analytical solution I need the inlet conversion. This is the value that we calculated. This was this. I can show you. So this is the value of 0.667. Okay. Continue. So this is just the analytical solution. So you can see here that I need a reactor size of 7.87 cubic meters. So this is a quite good agreement what we have, what I showed you in the last video with my analytical solution. Okay, then we need some initial values. I need some mole flows. Here I said, so if you think about it, then maybe you understand that you can say no conversion means that at the outlet of our reactor, if you have R+1 times the initial mole flow, then you have no conversion at all. And for the mole flow of B and C, I'm just saying it's 0. And then I have to, here for the while loop, I have to define two values for my conversion. Okay, here you can see this is the loop for the recycle block, and so in DVSim it would be something like a recycle block. Here I check if my conversions, the old one and the new one, if they are the same. And then what I'm just doing here is that I'm saying, okay, the inlet mole flow is just the initial mole flow plus the mole flow, the minimum value of the mole flow that is present inside the reactor. So since you know your mole flow here, where is it? This one. Since A is continuously decreasing and B and C are constantly increasing, I'm just saying find me the minimum value of my mole flow, and this is the mole flow at the outlet. So I was just a little bit lazy to say, okay, just grab the minimum. And I showed you that the mole flow coming back through the recycle is R over R+1. So, and then here I mix the mole flows, and I do the same with the mole flows for B and C. So this is the volume flow times the inlet concentration, and then I'm just adding the maximum value of component B, or the mole flow of B and the mole flow of C, and then I'm calculating the inlet conversion with the equation that I showed you already. Okay, what I also did here to make it more obvious, I'm saying, okay, I know in advance that my reactor should be 7.78. So this should be the volume of my reactor. And then here I'm just saying, okay, now let's calculate what's happening inside the reactor until we reach the volume of 7.87 cubic meters. and then I'm just playing around until we reach convergence. So if you want to go for a conversion of exactly 80% at the outlet, then you could implement it as an additional while loop or whatever, but this would make the code not so easy to understand. Okay, then we go for our iteration loop, or for our plug flow simulation. So here I'm just saying this is the volume of my reactor. I calculate the volume flow, then I calculate the concentration, I calculate the reaction rate. With the reaction rate I calculate the concentration and the change in mole flows. Then I update my mole flows, and with this I update my conversion. Then I increase my integration counter, and basically that's it. And then I have to where is undo? There. So here I'm just saying, okay, I'm setting my xalt or xold is the old value of the outlet conversion, and then I'm saying, okay, the new conversion is the last conversion that we calculated up here in our loop. Okay, and basically that's it. Then it's just plotting, and with this I get this. So, and how can you find the right conversion of 80%? So maybe you can first start with the volume of your reactor with 8 cubic meters. And then you will have a conversion of a little bit more than 80%. Okay, to make it more obvious, let's go for 9. So here you can see it more clearly. If you go for a volume of 9 cubic meters, then you will have a conversion of 82%. If you start with a volume that is too little, then you have a conversion at the outlet of only, what is it? No. Then you have a conversion of only 70%. And that's how you can play around. 7.87. And if you have this, then you have quite good value for your conversion of 80%. Okay, what else can we see? We can see here that this is our mole flow through the reactor, and we have at the outlet we have a mole flow of component C of 180 kilomoles per hour. Or maybe I can just copy this here and put it, copy figure. Then we can put it here. Okay. So what you can see here is that we have a mole flow of component C of 180 kilomoles per hour. But what does it mean? You have to remember that here, plug flow reactor, R is equal to 5. This means if you have, so this is here at the outlet of your reactor, And if you want to know what is your volume flow of your mole flow of component C, that is really leaving the total reactor, so then you can calculate it by n.c how to write it. This should be n.c reactor is 180 kilomoles per hour, and so your mole flow leaving the reactor, this is just 1 R plus 1 times n.c reactor so it's 1 over 5 plus 1 times 180 kilomoles per hour, so this is 1/6 of 180 kilomoles per hour, and this is 30 kilomole per hour, and this is what was given in your worksheet. So the task of this reactor was to produce a mole flow of component C of 30 kilomoles per hour. Okay. Yeah. I put my MATLAB code. I will put in the email room. I also created a second MATLAB code. So this was the first one, but there I used some more information about this, and there automatically the correct conversion is calculated. But I think the code that I showed you here is more easy to understand, hopefully. Okay. Thank you for watching, and see you in the next video.